Now this is your typical series parallel circuit. This one contains 9 resistors arranged in a series parallel arrangement. Couple of things to note about this before we start. Here we have 5 ohms. This one down here, 8 ohms that should be. Now, before we start this, we think about the fact that our source is over here at 50 volts, and generally we have that applied to the circuit but not to any resistors individually. And so we have the resistance value of each resistor, but we don't have 2 pieces of information about any of the resistors or the circuit. And so we have to start by saying that if we had the total resistance of the circuit, then we'd have 2 pieces of information about the circuit, namely the resistance and the voltage applied, so that would allow us to calculate the total current. And so we will start then by systematically reducing the circuit to find the total resistance, which is very often the starting point for all of these series parallel circuits. We have also been asked to find the current through resistor R2 or I2, which is labeled here on the circuit. We've been asked to find the current through resistor R4, which is labeled here on the circuit, and the voltage across resistor R6, which is labeled here on the circuit, and of course the total current. Now, one of the things that you might find makes this a little bit easier is we generally define each point in a circuit with 3 or more resistors connected to be a junction or a node. In this circuit, then, you may wish to label the nodes as, for example, A, B, and down here at the bottom, then let's say node C. And so if you think about the voltage between points B and C would be the voltage across R6 or across the combination R7, 8, and 9 in series. And so that very often is helpful in the solution of these circuits. Now, so we'll start then by identifying resistors, combinations of resistors that are in series or parallel. Very often you start on the right of the circuit, works your way back to the source. And so for this one, we have R7, R8, and R9 in series. We also can identify that R4 and R5 are in parallel because they are both connected to points A and B, which says they have the same voltage across them. And of course we can show that R2 and R3 are in series. And so thus we will complete those calculations and then redraw a simplified circuit or an equivalent circuit. Now, so then we can start by saying that R7 in series with R8 in series with R9 is equal to 4 ohms plus 6 ohms plus 8 ohms is equal to 18 ohms. So 18 ohms is equivalent to R7, R8, and R9 in series. We have R4 in parallel with R5, and we could use the reciprocal formula to determine the total of that resistance. But remember, one of our shortcuts was when there's only 2 resistors in parallel, we can say that the equivalent resistance is equal to the product of R4 times R5 over the sum R4 plus R5. And that will allow us to say 12 ohms times 6 ohms over 12 ohms plus 6 ohms, or 72 divided by 18, and that gives us an equivalent value of 6 ohms. In addition then, that gives us actually an equivalent value of 4 ohms. Now, in addition, we had R2 in series with R3, and that is 7 ohms plus 3 ohms equals 10 ohms. So now we can redraw the circuit, replacing the resistors we've identified in the first circuit with their equivalent values. Okay, so you'll notice that I've inserted a graphically drawn circuit whereby I have replaced R7, R8, and R9 with the 18 ohm value. I have replaced R2 and R3 with the 4 ohm value. I have, replaced R4 and 5 with the 4 ohm value, replaced R2 and R3 with the 10 ohm value. Now, in addition to that, we still have labeled on this circuit V6, I2, and IT, and we've also labeled this current here as I4 ohm. The original current I4 is part of that I4 ohm current. Now, continue our analysis by identifying resistors that are in series and parallel. Well, these two here are in parallel. Now remember the nodes that we had: node A, node B, and now at the bottom all the way across there would be node C. And so again, the R6 and the 18 ohm value here are both connected between nodes B and C, therefore they will have the same voltage across them, and so we conclude that means they are in parallel. Okay, so we have then R6 in parallel with 18 ohms is equal to 9 times 18 over 9 plus 18, and that gives us 162 divided by 27, or 6 ohms. Now, you might be able to realize at this point that the 4 ohm value here is in series with this 6 ohm value. If not, redraw the circuit again. And so very often when I redraw the circuit, the symbol for the source over here, I will put it in as a circle with a plus minus sign in it. They're equivalent, really. And so if we do that, then we have E at 50 volts. We have not included R1 in any calculations yet, so we should include R1 at 5 ohms. We should include the 10 ohm value, which represents R2 and 3. We should include the 4 ohm value, which represents R4 and 5. And now we have an equivalent value between nodes B and C of 6 ohms. We can still say that node A, node B, and node C exists in this circuit. Really, node B now only has 2 resistors connected to it, so it's not really considered a junction or node, but we still can label it in our circuit. In addition, we can label IT, still have I2 in here, and remember V6 was the voltage between points B and C, and so we can still show that on this circuit. Now, so then the 4 ohm value and the 6 ohm value now are in series, which means that we have 4 ohms in series with 6 ohms, or 4 plus 6 equals 10 ohms. Now, you may want to redraw the circuit again at this point, or continue simplifying it if it is apparent that this new 10 ohm value is in parallel with this 10 ohm value. I will redraw it again. Okay, now then, we have inserted the next circuit, and we can identify in this circuit node A, and still, of course, node C. Now, this circuit still contains the I4 ohm, as you see labeled here. I2 and IT, of course, still apparent in this circuit. Now, in this circuit, both the 10 ohm values are connected between nodes A and C, and therefore we can say that these are in parallel. We have now 10 ohms in parallel with 10 ohms, or 10 multiplied by 10 over 10 plus 10 gives us 100 over 20, or an equivalent value of 5 ohms. Now that 5 ohms is in series with R1 for the final calculation, and I will redraw it again. You may not believe that that is necessary, but in any event, E here at 50 volts. We have now R1 at 5 ohms, and the 5 ohm value that represents now the other 8 resistors that we have simplified or reduced to a simple 5 ohm value. From here now, we can say that RT is equal to 5 ohms plus 5 ohms, or RT equals 10 ohms. Okay, now, generally, at this point, what we will do is we have kept our calculations now for equivalent resistance on the left side of the page, and so one of the techniques you might find useful is that now you can go and start at the bottom right side and analyze the equivalent circuits we've drawn to work our way back up to the top and complete parts B, C, and D as we go. And so first then we will calculate now IT, and part A then we can say that by Ohm's law IT is equal to E divided by RT, and we have 50 volts over 10 ohms, or 5 amps for IT. Okay, so now we have a current of 5 amps that flows through these two resistors. Ohm's law will tell us that as 5 amps flows through this 5 ohm resistor, we get 25 volts across it. In addition to that, then KVL, or Ohm's law, tells us 25 volts here. And so generally we can conclude that the voltage drop across both of those 5 ohm values will be equal to the current multiplied by the resistance, and in this case IT, 5 amps times 5 ohms, or 25 volts. Now, because the two resistors are equal and in series, then they will have equal voltages across them. Okay, so these calculated values will be valid for all of the circuits that we have redrawn. And so basically what we're saying then is that this 25 volts here is the voltage between points A and B. Remember that these two 10s made up the 5 ohm value. If the voltage drop across this 5 ohm value is 25, then the voltage between points A and C is 25. What that means is that the voltage drop across resistor 2 is equal to 25 volts. Therefore, the current I2 by Ohm's law, V2 divided by R2, we have 25 volts divided by 10 ohms, or I2 is equal to 2.5 amps. And that is the answer for part B. Now, if you think about our circuit then, we have 5 amps enters at IT. It will enter node A here and become 2.5 amps, and I2 at 2.5 amps. So basically what we're saying now is that if we move this up a little bit, Kirchhoff's current law tells us that IT equals I2 plus I4 ohm, if I can fit that in there. So the current through the 4 ohm resistor is IT subtract I2, and we have 5 amps subtract 2.5 amps, and I4 ohm equals 2.5 amps. Now sometimes you don't need to do the calculations. If you have a bunch of circuits redrawn, you can see that these calculations apply to your redrawn circuits. And so now we had then right here I2 2.5 amps, the current through the 4 ohm then at 2.5 amps. And so as we move back up to our redrawn or more complicated circuits, you will find that we have to move the values we have calculated for the simplified circuits to the larger circuits. And so if the current through the 4 ohm resistor is 2.5 amps, that means that I6 ohm equals 2.5 amps. That allows us then to say that the current that flows through this branch at 2.5 amps means that V6 is equal to the current I6 ohm times, of course, the 6 ohm value, or 2.5 amps multiplied by 6 ohms, and that V6 then is equal to 15 volts. And that was the answer actually to part D. Now, as we move up now, we find that we must go back to the more complicated circuit, the one we started with, to find I through resistor 2 or I2, because that is the only one really that it shows up on. And so now remember that the current through the 4 ohm right here was 2.5 amps. And if you'd wish to use current division now, you can divide that current between resistors 4 and 5. However, what we'll do is, back in the original circuit now, we can say that the voltage drop across the here is VAB, and VAB is equal to the current I 4 ohms multiplied by the resistance 4 ohms. And so remember that in one of these circuits down here, the voltage drop between points A and B is the voltage drop across that 4 ohm value. And so VAB is equal to I 4 ohms times 4 ohms, whichever way you look at it. We have 2.5 amps times 4 ohms, and VAB is 10 volts. And so if VAB is 10 volts, as we move back up here, we can say that V4 is equal to 10 volts. The current I4 then, by Ohm's law, will be given as V4 divided by R4. And we have 10 volts divided by 12 ohms, and I4 then has a value of 0.833 amps, and that is the answer to part C. Now, just to recap, we would like to say that we need to identify the things we are asked to find. We should label those on the circuit. We should complete our solution then aimed at finding the things we've been asked to calculate. We need to typically find the total resistance, which involves identifying series and parallel resistors or branches and finding their equivalent resistance. Very often, start at the right side of the circuit, work your way back to the source. Then, as we complete the calculations, we identify the equivalent circuits, the equivalent resistance values rather, we redraw the circuit until we have simplified it to the point where we have calculated the total resistance in the circuit, and in this case, of course, 10 ohms. Then we wish to use our simplified circuits along with Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law to complete the calculations we've been asked for. In this case, part A, odd T, part B, odd 2, and then we did part D first because that's what was easiest for us to do. Part D then, V6, and finally part C where we found I4.